Welcome to TalkTensors. So today we are doing a deep dive into something that, frankly, it sounds a little bit like science fiction.
Oh, absolutely. It really does.
Back in 2016, Google decided to try and solve one of the absolute hardest, most frustrating problems in all of computer science.
Yeah, they wanted to build a better, just a much more efficient artificial intelligence.
Right. But instead of putting their absolute smartest human engineers in a room with a whiteboard to design this thing.
They didn't do that.
No, they didn't. They asked an AI to design it for them.
Exactly.
So today we are looking at this exact moment when machines basically started building themselves.
It is a genuinely historic piece of research for you to know about. We're talking about the paper called Neural Architecture Search with Reinforcement Learning.
Right.
It was published by Barret, Zoph, and Quoc over at Google Brain.
Right.
And, to really understand why this paper just sort of hit the machine learning community like a meteor.
Which it did.
Oh, it completely did. But we have to kind of rewind the clock a little bit. We need to look at the historical context here.
Yeah, let's set the stage.
Right. So the state of the art in the early 2010s had just gone through this massive, really painful paradigm shift.
Painful is a good word for it.
Yeah, because for years, the entire field was just absolutely obsessed with this concept called feature engineering.
Okay, let's paint a picture of what feature engineering actually looked like for, say, a grad student back then.
Oh, it was not glamorous.
Not at all. I mean, it was rough. You had these PhDs spending months or literally years sometimes just writing incredibly specific mathematical algorithms.
Yeah, things like SIFT or HOG.
Right, exactly. So if you wanted your AI to recognize a car, the AI couldn't just, look at a picture of a car and figure it out.
No, a human literally had to mathematically define what an edge was.
Right, or what a corner looked like. Or even how light gradients shifted across a metallic surface.
You were basically handcrafting the very lenses through which the computer saw the world.
Yeah, and it was just grueling work.
I mean, a researcher might spend an entire year just tweaking one mathematical filter.
Right, just to get a 1% improvement in recognizing a dog versus a cat.
Exactly. But then, the deep learning revolution finally arrived.
Thank goodness.
Yeah, papers like AlexNet completely upended the table. The whole philosophy of deep learning was just stop handcrafting the features.
Right. Instead, they were let's just build a massive layered neural network, feed it 1 million images, and let the network figure out what an edge is entirely on its own.
Yeah, and it worked. So we moved from feature engineering, right, to architecture engineering.
Architecture engineering.
Yes. So models like VGGNet, GoogleNet, and the whole ResNet family, they proved that if you just provided the right structural blueprint, the AI would learn the features better than we ever could.
It was a total revelation.
It felt like liberation, honestly. But almost immediately, the community realized they had just kind of traded one impossible problem for another.
Yeah, let's use an analogy here for you listening. Think of this transition sort of like the Industrial Revolution.
Okay, I like that.
Right, so for decades, we were these artisans making individual car parts by hand with tiny little tools.
That's the feature engineering.
Exactly. Then deep learning comes along and we say, no more hand tools. We are going to build massive automated factories to do the work for us.
And those factories are the neural networks.
You got it. But there's a huge catch here. We still needed human master architects to design the actual factory floor plans.
And man, designing those floor plans required this immense, almost esoteric level of expert knowledge.
Absolutely. You had engineers just staring at screens wondering, should we put a pooling layer here?
Or what if we change the convolution filter from a 3x3 grid to a 5x5 grid?
Should this layer connect to the next one or skip 2 down?
It was entirely based on human intuition.
And trial and error. Lots of trial and error.
So much. And frankly, a lot of luck. It was incredibly tedious, and it was becoming this massive bottleneck for the entire industry.
Which brings us to the core breakthrough of this paper by Zoph and Lee.
Right. They looked at this bottleneck, these highly paid human engineers just sort of guessing at floor plans, and they posed this radical, basically one-sentence thesis.
And what was that?
They said, what if we used a neural network to search for and design the architectures of other neural networks?
See, that just sounds like the prequel to the Terminator.
It does.
But it's very real. And the methodology they use to actually achieve it is just absolutely brilliant.
It really is.
So what is our mission for this deep dive today?
Well, we are going to explore the exact mechanics of what they termed neural architecture search, or NAS.
NAS. Okay.
Yeah. We will translate all that heavy math of reinforcement learning into plain English so you can understand how they trained this system.
And we're going to look at the staggering results they achieved on these benchmark tests, right?
Oh, yeah. And finally, we will trace the massive legacy, this single paper left on the AI frameworks we still use today.
You are definitely going to want to stick around for this one.
So to get started, we need to introduce the sort of central mechanism of their approach.
Right. How does it actually work?
Well, the authors realized that the physical structure, the connectivity of any neural network can essentially be translated into a sequence of text.
A sequence of text. Interesting.
Yeah. And because of that observation, they decided to build their system around what they call a controller.
Okay, a controller.
And they built this controller using a recurrent neural network, or an RNN.
Let's visualize what this controller is actually doing. Its entire job is basically to spit out a sequence of instructions, almost like a recipe, right?
Exactly like a recipe.
And those instructions act as the blueprint for a brand new, totally experimental neural network, which the paper refers to as the child network.
That is the exact function of the controller. It generates these architectural hyperparameters autoregressively.
Autoregressively. Let's break that down.
Yeah, so that means it predicts the blueprint one specific piece at a time. And every new choice it makes is heavily influenced by all the previous choices it just made in that sequence.
Oh, I see.
They actually borrowed this concept from the world of machine translation. Specifically, the decoders used an end-to-end sequence-to-sequence learning.
Okay, so if I am the controller, and my task is to design a standard convolutional neural network for, say, recognizing images.
Right.
I don't just magically output a fully formed model in one go.
No, you have to go step by step.
Right. So I output a token for the first filter's height. Maybe I choose a 5.
Okay.
Then I have to choose the filter's width. So I pick another 5.
Yeah, making a 5x5 filter.
Exactly. Then I decide the stride height, the stride width, and exactly how many of these filters should even exist in layer 1.
And once you've made all those decisions for that first layer, you loop back around.
Right, and do the exact same thing for layer 2 and then layer 3 and so on.
And at each of those steps, the controller is calculating a probability distribution over all the possible choices it has.
Like deciding between options.
Yeah. It looks at the options like, should the filter be a 1, a 3, a 5, or a 7? Mm-hmm. And it assigns a percentage to each one.
Interesting.
It picks one, and that choice immediately becomes the context for the very next decision. Yeah. It is literally building the architecture piece by piece.
But wait, let me pause you right there, because if I'm a researcher listening to this back in 2016, I'm going to be pretty skeptical.
Sure, why?
Well, hyperparameter optimization wasn't exactly a new concept, right? We already had algorithms dedicated to finding the best settings for models.
That's true, we did.
People were using grid search, where you basically just test every single combination in a massive spreadsheet.
Right.
And they were using Bayesian optimization, which is, much smarter. It predicts which settings might work best based on past tests.
Right. Bayesian was very popular.
So why go through the massive headache of training an autoregressive RNN to do this? Isn't this just a wildly overcomplicated version of a grid search?
That is the exact criticism a lot of people had initially when this came out.
I bet.
But if we look closer at those older methods, we see this really fatal flaw when it comes to true discovery.
What's the flaw?
Bayesian optimization and grid search are almost always restricted to searching within a fixed length space.
Oh.
You, the human, have to define the boundaries before the search even begins.
Right. So you have to tell the algorithm, hey, I'm going to build a network with exactly 5 layers.
Yes. You say, please find me the best filter sizes for those 5 specific layers.
I see the problem. By defining the box, you're artificially limiting the potential of the model before it even boots up.
Exactly.
You're bringing human bias into the search.
Yes, you are telling it what the ceiling is. But an RNN generating a variable length string of tokens, it doesn't have a ceiling. The controller can decide dynamically, like right on the fly, exactly how deep or how complex a network needs to be. It has no strict predefined limits on the architecture's depth.
That's incredible.
In fact, the authors designed this schedule where, as the training progresses, they slowly allow the controller to increase the number of layers it's allowed to generate.
It's like telling a construction crew to build a tower, but instead of giving them a blueprint that says stop at 10 floors,
Right.
you just give them an infinite supply of bricks and let them decide when the tower is tall enough to serve its purpose.
That open-ended flexibility is the secret sauce here.
It really is.
It is what allows the system to discover completely novel, totally bizarre architectures that a human would just never have explicitly programmed into a rigid grid search.
Okay, so now we have our controller, and it is generating these variable length blueprints.
Right.
But, I mean, a blueprint is totally useless until you actually test it.
Absolutely.
Which brings us to the actual training loop. And this introduces the core mathematical challenge of the entire paper.
Yeah, this is where it gets really interesting.
So once the controller spits out a design, the system physically compiles that design into a real child network.
It builds it.
It builds it, it initializes the weights, it takes a data set, say tens of thousands of images of airplanes and birds, and it trains that child network until it learns as much as it can.
And then what?
Then it tests the network on a separate set of images to see how well it actually performs in the real world.
And the resulting accuracy of that child network, let's say it gets 85% of the images correct. That score becomes the reward signal.
The reward signal.
Yeah, the paper refers to this reward as R. The system takes that 85% and feeds it right back to the controller to tell it how good its blueprint was.
Makes sense. But here is where we hit a massive wall.
A huge wall.
In standard deep learning, when you want a neural network to improve, you use a process called backpropagation.
Right, backprop.
You calculate how wrong the network's prediction was, and you use calculus, specifically derivatives, to trace that error backward through the network.
You're adjusting all the little mathematical knobs so it does better next time.
Exactly. But backpropagation relies on smooth, continuous curves. It requires the error to be differentiable.
And that's the problem. Because accuracy is not a smooth curve.
No, it's not. Accuracy is a step function. You either classified the image of the bird correctly or you didn't.
It's totally binary.
It's a staircase, not a smooth hill. You literally cannot take the derivative of the network scored 85%.
Exactly. Because the reward signal R is non-differentiable. Standard backpropagation is just completely impossible here.
You cannot use the standard toolkit of deep learning to update the controller's internal weights.
No, you can't.
So we have a controller that desperately needs to learn, but the standard way of teaching it is mathematically broken. How did Zoph and Les solve this? How do you update the controller without a gradient?
Well, they had to step entirely outside of traditional supervised learning. They turned to reinforcement learning. Specifically, they utilized the reinforce rule, which is a policy gradient method introduced by Ronald Williams way back in 1992.
Wow, 1992.
Yeah, and the objective of the controller here is simply to maximize its expected reward over time.
Okay, let's translate the math of the reinforce rule into something more mechanical for you listening.
Good idea.
We want to maximize the expected value of R, but we can't differentiate it. So the system uses an empirical approximation.
Right.
Instead of dealing with derivatives of the actual accuracy, the system looks at the controller's confidence.
That's a really great way to frame it.
Thanks.
The reinforce equation basically calculates the gradient of the log probability of the predicted actions.
Which means?
Which is essentially a measure of how strongly the controller believed in the specific sequence of architectural tokens it just chose.
Ah, I see.
It then multiplies that confidence by the real-world reward.
Let me make sure this mechanism is perfectly clear. The controller guesses a blueprint. It's maybe 60% confident that this is a good idea. Okay. The system builds it, and the network gets a massive reward, say 95% accuracy.
A huge success.
Right. So the equation takes that high reward and multiplies it by the controller's decisions. It is mathematically whispering to the controller, hey, that sequence you just generated, it was amazing.
Whatever you did, increase your internal probabilities for those specific choices.
Be more confident about those filter sizes next time.
Exactly. And the inverse is also true.
Right, if it fails.
Yeah, if the controller proposes an architecture and the resulting child network gets a terrible accuracy of like 20%, the reward is very low.
So the math tells the controller to suppress the probabilities of those choices.
Yes. Over thousands of iterations, just through sheer trial and error, the controller's internal probability distributions start to shift toward architectural patterns that yield higher and higher validation accuracies.
But anytime you bring up the reinforced algorithm in machine learning, you have to talk about its biggest flaw.
Oh, the variance.
It suffers from a massive variance problem.
It really does. While the update rule provides an unbiased estimate of the gradient in theory. In practice, the updates just bounce around chaotically.
Let's explore why that happens, because it's important. Imagine the controller proposes a new child network, and it gets an accuracy of 80%.
Okay.
Is 80% a good reward or a bad reward?
Well, it depends, right?
Exactly. If the previous 10 networks the controller designed only got 30% accuracy, then 80% is an incredible breakthrough. The controller should be heavily rewarded.
Yeah.
But if the previous 10 networks were getting 95% accuracy, then a new network scoring 80% is actually a huge step backward.
It's a failure.
Right. If you just multiply the confidence by the raw number 80 in both of those scenarios, the controller gets totally confused. It's basically being rewarded for getting worse.
Yeah.
The learning process destabilizes.
So to solve this variance problem, the authors incorporated this really critical stabilizing element into the math.
What did they do?
They introduced a baseline function, which they denote in the paper as B.
Think of this baseline function kind of like grading on a curve. How does B actually change the math?
In this framework, the baseline B is calculated as an exponential moving average of all the previous architecture accuracies.
So it's a running tally.
Exactly. It's a running tally of how well the controller's been performing recently.
Okay.
When they do the reinforce update, instead of just multiplying the controller's confidence by the raw reward R, they multiply by the quantity R minus B.
They subtract the recent average from the current score.
Yes.
That is incredibly elegant.
It completely changes the incentive structure.
Right, because now if the controller builds an 85% accurate network, but its recent moving average B is 90%, the result of R minus B is -5.
The update becomes a penalty.
The controller is actively punished for doing worse than its own recent standards, even if the raw score of 85% looks okay in a vacuum.
It forces the controller to constantly compete against its own history.
That's brilliant.
And this stabilization is what allows the RNN to smoothly climb the performance ladder instead of just thrashing around randomly.
So conceptually, the reinforcement learning loop is solved.
Yep, the math works.
But practically, actually executing this loop introduces a complete logistical nightmare.
Oh, absolutely.
I was just thinking about this. The compute requirements we're talking about here are mind-boggling.
They are massive.
Training just one modern neural network on a large image dataset can take days on a high-end graphics card.
Easily.
To train this controller, you are asking it to generate, build, fully train to convergence, and evaluate thousands upon thousands of child networks.
It's a lot.
If you tried to run this on a single computer, you would be waiting centuries for a result. How did Google Brain pull this off in 2016?
This really highlights a crucial subtext of the paper. The shift of AI research toward massive infrastructure.
Yeah, right.
They had to rely on distributed training at a completely unprecedented scale. They utilized a parameter server scheme with asynchronous updates.
Let's break down the physical architecture of how they actually ran this experiment. The paper gives us the exact hardware layout for their image recognition task.
What was the setup?
They set up 20 parameter server shards.
20 shards, okay.
And these 20 servers had one job: store the master copy of the controller's weights. Then they deployed 100 separate controller replicas across their network.
Wow. And each of those 100 replicas was assigned to sample 8 different child architectures at a time.
Let's do the math on that.
Well,
100 replicas, each building and training 8 separate neural networks.
that's 800.
That means at any given moment, there were 800 distinct neural networks being trained concurrently across 800 high-end GPUs.
Yes. And the key word you used earlier is asynchronous.
Right.
These 100 replicas are not waiting for each other to finish. It is a continuous, relentless process.
They just keep going.
As soon as one replica finishes training its batch of 8 child networks, it calculates the policy gradient updates based on their accuracies. It sends those updates to the parameter servers, which adjust the master weights. The replica then immediately downloads the newly updated master weights and instantly starts generating its next batch of 8 architectures.
It's like an ultra-competitive corporate environment.
That's a great way to think of it.
Imagine 100 different architectural firms working in parallel. Each firm has 8 junior draftsmen furiously building experimental skyscrapers.
Okay, I see it.
Every time a skyscraper is finished, they subject it to an earthquake test. If it survives, the firm instantly calls the central headquarters and says, hey, we found out that reinforcing the third floor with titanium works really well.
And headquarters immediately updates the master corporate design manual.
Exactly. So by the time the next firm starts drafting their next building, they already have that titanium insight incorporated into their thinking.
It is an automated, nonstop engine of scientific discovery.
It really is.
And they needed every single ounce of that massive compute engine because the search space they were exploring was about to get exponentially more complicated.
Oh, right. Because up to this point in our discussion, we have only talked about the controller generating simple, feed-forward convolutional networks.
Right, straight lines.
These are networks where layer 1 connects to layer 2 connects to layer 3, just in a straight, linear path.
But we both know that by 2016, straight-line networks were already pretty obsolete.
Yeah, human engineers had already moved on.
The top-tier models of the day, like GoogleNet and the incredibly famous ResNets, they didn't look like straight lines.
Not at all. They look like tangled webs.
Yeah, they featured branching paths and, most importantly, skip connections.
A skip connection is where the output of layer 2 might bypass layers 3 and 4 entirely and wire directly into layer 5.
Right. These shortcuts allow networks to train much deeper without losing information.
So if our AI controller can only build simple straight lines, it is going to lose to human engineers every single time.
You wouldn't stand a chance.
How do you get an autoregressive RNN, which generates tokens in a strict sequence, to invent branching skip connections?
This is one of the most elegant engineering solutions in the entire paper, honestly.
What did they do?
The authors integrated a mechanism they called set selection type attention directly into the controller.
Set selection type attention.
Yeah. They borrowed this concept from the attention mechanisms that were just beginning to revolutionize natural language processing at the time.
Let's translate that attention mechanism into something we can visualize. No complex math equations. How does it physically decide to route the data?
Imagine the controller is currently in the process of generating the design for layer number 5.
Okay, I'm at layer 5.
As it is making its decisions, the system introduces an anchor point.
An anchor point.
Right. At layer 5, this anchor point contains 4 internal probabilistic switches, one for every single layer that came before it.
So it pauses its forward momentum and looks backward.
Yes.
The controller looks at its internal memory state from when it designed layer 1, compares it to its current state at layer 5, and runs a calculation.
And this calculation spits out a probability score between 0 and 1.
Correct. It uses a combination of trainable matrices and a sigmoid activation to compare those hidden states.
Right.
And if the resulting probability score crosses a certain threshold, the controller effectively flips the switch and says, yes, I'm going to build a physical bridge connecting the output of layer 1 directly into layer 5.
And then it just repeats this calculation for layer 2, layer 3, and layer 4.
It is dynamically deciding the topology of the network right on the fly.
Yeah. And because these decisions are all based on probability distributions, the reinforced algorithm we discussed earlier still functions perfectly.
Oh, that's true.
If a weird tangled skipped connection results in a higher accuracy, the system will reward the controller for flipping those specific switches.
But wait, I have to push back here because this sounds incredibly dangerous from a software engineering perspective.
Really? How so?
If you give an AI the freedom to just randomly flip switches and connect any layer to any other layer, isn't it going to build absolute garbage most of the time? Like, what if it generates a layer but decides not to connect its output to anything? It's just a dead end.
Right.
Or what if it decides a middle layer shouldn't have any inputs at all? In normal coding, that throws a fatal error. The program crashes.
It would.
And you cannot train a broken neural network, which means you get no accuracy score, which means the reinforced loop completely breaks down.
That is a highly astute observation, and the authors anticipated exactly that problem.
They knew it would crash.
They knew they would encounter what they called compilation failures. So to prevent the system from crashing, they engineered 3 specific fallback rules.
Oh, okay. Guardrails.
Exactly. These are basically guardrails built into the compiler to ensure that no matter how bizarre the controller's design is, it will always result in a mathematically valid, runnable network.
Okay, let's look at those guardrails. What is the first rule?
The first rule addresses the missing input problem you mentioned.
Right.
If the controller generates a layer but fails to connect any previous layers to it as an input, the system automatically intervenes.
What does it do?
It uses the original raw dataset image as the input for that orphaned layer.
Oh, that makes perfect sense. It's a safety net, so no layer ever starves for data.
Exactly.
What about the dead ends?
That's the second rule. As the compiler finishes building the network, it scans the entire architecture for any layer outputs that haven't been connected to a subsequent layer.
It hunts them down.
It gathers all of those hanging dead-end outputs, concatenates them all together into one massive tensor, and feeds that combined data directly into the final classification layer.
So nothing the network computes is wasted.
Not a single thing.
Brilliant. But that brings up the third and, frankly, the hardest problem, dimensional mismatch.
Ah, the matrix math.
Right. If the controller decides to connect layer 2 to layer 5, but layer 2 is outputting a massive 32 by 32 feature map, and the rest of layer 5's inputs are tiny 8 by 8 feature maps, you can't add those together.
The matrix math literally doesn't work.
The dimensions are completely incompatible.
The third rule handles this seamlessly. If the system needs to combine input layers that have different spatial sizes, it automatically applies zero padding to the smaller layers.
Zero padding.
Yeah, it just adds borders of zeros around the smaller feature maps until they match the exact dimensions of the largest feature map in the group.
And then?
Then they can be concatenated without throwing an error.
Zero padding. It is such a simple trick, but it is incredibly robust.
It saves the whole operation.
These three guardrails basically guarantee that the controller has a completely safe playground.
Yeah, it can experiment with the most chaotic, totally non-intuitive wiring diagrams imaginable.
And the system will faithfully compile it, train it, and return a reward signal.
And that robust playground allowed the authors to push the system even further.
Where do they take it next?
In the next major phase of their research, they wanted to prove that neural architecture search wasn't just like a gimmick for image recognition.
Right, they wanted to show it was a generalized, fundamental tool.
So they completely pivoted. They shifted from designing convolutional neural networks for images to designing recurrent neural networks for language tasks.
Now, this is a massive leap.
Oh, a huge leap.
Designing a CNN is mostly about spatial grids, but a recurrent cell, like the industry standard long short-term memory cell, or LSTM, deals with time and sequential data.
Exactly.
At every single time step in a sentence, a recurrent cell has to take the current input word, combine it with its hidden memory of the previous words, and process them through a very intricate human-designed arrangement of mathematical gates.
Just to produce a new memory state.
Right. How on earth do you get an RNN controller to invent a new microscopic memory cell from scratch?
They had to change the search space entirely. They basically abstracted the internal workings of a recurrent cell into a tree of mathematical computation steps.
Tree.
Yeah. The controller doesn't just predict a sequence of layers anymore. It actively traverses the nodes of this tree.
Let's visualize this tree indexing method for the listener. They use what they called a base 8 tree to represent the wiring inside the cell.
Okay.
The controller visits the first node in this tree, and at this node, it has to make two distinct predictions.
What's the first one?
First, it must choose a combination method. Should it take the two data streams and add them together, or should it use element-wise multiplication?
Okay, and the second prediction?
Second, it must choose an activation function to apply to that result. Should it pass the data through a hyperbolic tangent, a sigmoid, a real U, or just leave it as an identity function?
And remember, an RNN needs to manage long-term memory.
Right, the memory states.
It isn't just combining the current input and the immediate past. The cell utilizes memory states, denoted as C.
Yes.
During the final steps of its sequence, the controller specifically predicts exactly where in the computation tree it should inject these long-term memory variables.
It dictates the actual flow of memory through the cell. When you combine all of these decisions, a base 8 tree, choosing between different combination methods, selecting from multiple activation functions, and deciding the exact injection points for memory, the mathematical combinatorics absolutely explode.
Explode is putting it lightly.
The authors calculated the sheer size of this specific search space.
Yeah.
For this single task of designing a recurrent memory cell, there are 6 times 10 to the 16th power possible architectures.
That is 60 quadrillion different ways to wire the inside of a single neural cell.
60 quadrillion. We do not have enough GPUs in the known universe to grid search 60 quadrillion combinations.
Not even close.
It is physically impossible to test them all.
Which is exactly why the reinforcement learning approach is so vital here.
Right, because the controller didn't need to test 60 quadrillion networks.
No, by following the policy gradient, by constantly updating its probabilities based on that R minus B reward signal we talked about.
It navigated that unfathomably massive space with surgical precision.
It really did. Over the course of the experiment, the controller only physically built and evaluated 15,000 architectures.
Out of 60 quadrillion possibilities, it only looked at 15,000.
Yeah.
And within that tiny fraction, it found a global optimum that outperformed human engineering.
That is staggering efficiency.
It really is. It completely validates the premise that the controller isn't just, randomly guessing. It is genuinely learning the underlying laws of architectural physics.
Absolutely.
So this brings us to the ultimate question. How good were the machines it actually built?
Let's dive into the experimental results.
What did they discover, and how did it compare to the best human minds? Let's start with their first task on the CIFAR-10 image dataset.
The results on CIFAR-10 were just a watershed moment for automated design.
Tell us about it.
When given the freedom to predict skip connections and pooling layers, the controller ultimately converged on a bizarre, highly complex 39-layer convolutional network.
39 layers.
And the structure of this network defied standard human logic completely.
In what way?
For instance, the controller selected a progression of filter sizes that no human would ever intuitively choose: 6, 12, 24, and 36.
See, humans like clean, symmetrical numbers.
You do.
We like powers of 2, 32, 64, 128.
But the AI chose 36 because the math worked, aesthetics be damned.
And what happened when they fully trained this 39-layer alien structure?
The authors took this architecture, added more of these specific filters to increase its overall capacity, and tested it.
Yeah.
It achieved an astounding 3.65% error rate on the CIFAR-10 test set.
3.65%. Let's contextualize that for the era. In 2016, what was the absolute pinnacle of human-invented architecture on this exact data set?
At that time, the state-of-the-art model was a dense net, which had been painstakingly developed by top-tier researchers.
And what did it get?
The dense net achieved a 3.46% error rate.
So the AI-generated model was mere fractions of a percent away from the best human model in existence?
It is virtually tied.
But there is a crucial detail here. The AI's model was significantly more efficient. The paper notes that their 39-layer network was 1.05 times faster than the dense net. It achieved elite accuracy while consuming fewer computational resources.
And what makes this result so scientifically rigorous is that Zoph and Lay didn't just, publish the final score and walk away.
Right.
They conducted extensive control tests to understand why this specific alien architecture works so well.
They essentially performed surgery on the network.
They really did. First, they manually intervened and added dense connections between all the layers, basically treating it like a dense net.
And what happened?
The performance collapsed. The error rate jumped from 3.65% all the way up to 5.56%.
And what if they went the other way? What if they took a machete to the architecture and removed all the strange, tangled skip connections the controller had invented?
The model fell apart completely. Without the skip connections, the error rate plummeted to 7.97%.
That is fascinating. It proves that the controller had not just stumbled upon a lucky combination of filters. It had navigated the high-dimensional space and found an incredibly fragile, delicate, local optimum, a perfect balance of skip connections that human engineers, with all our bias towards symmetry and repeating blocks, had completely overlooked.
It found a mathematical harmony that we just couldn't see.
Exactly. So it conquered image recognition. But what happened when they unleashed it on that 60 quadrillion space of language modeling?
They tested their new RNN cell on the widely used Penn Tree Bank dataset.
Right. And in language modeling, performance is generally measured using a metric called perplexity.
For you listening, think of perplexity as a measure of how confused the AI is when trying to predict the very next word in a sentence.
Exactly. A lower perplexity score means the model is less confused and therefore much better at understanding the language. So what was a perplexity score of this AI-designed cell?
The recurrent cell discovered by the controller, which the authors officially dubbed the nacelle, achieved a test set perplexity of 62.4.
62.4. And what was the reigning human champion at the time?
The previous state-of-the-art record was held by a highly complex model known as variational recurrent highway networks.
Okay.
Published by Zilli et al. Their perplexity score was 66.0.
So the nacelle didn't just match the human record, it obliterated it by 3.6 full points.
In the context of the Penn Tree Bank benchmark, dropping the perplexity by that much is a massive, definitive leap in performance.
And just like with the image model, the authors point out that the nacelle accomplished this while running more than twice as fast as the previous best network.
But the true hallmark of a revolutionary architectural discovery isn't just winning one specific benchmark.
Right. The real test is transfer learning.
Exactly. Can this nacelle be used for other tasks, or did the controller just brutally overfit its design to the specific vocabulary of the Penn Tree Bank dataset?
So how did they test that?
To prove its generalization, the authors took the exact same nacelle structure and applied it to a character-level language modeling task.
Right. So instead of predicting the next word in a sentence, the model is tasked with predicting the very next letter.
It is a completely different distribution of data and requires a different type of memory retention.
And the nacelle generalized flawlessly.
It did.
On the character level task, it set a brand new definitive state-of-the-art record of 1.214 bits per character, comfortably beating out heavily engineered human designs like the layer norm hyper LSTM.
But the crowning achievement of this paper, the real-world deployment that just cemented its legacy in the industry, was their final experiment.
Oh, this is the best part.
They took this nacelle, this weird mathematical structure generated by an RNN playing around on 800 GPUs, and they dropped it directly into a massive production-grade Google system.
Yes, they integrated the nacelle directly into the Google Neural Machine Translation Framework, commonly known as GNMT.
This was the flagship system Google utilized for translating English to German.
And the GNMT was a beast. It had been painstakingly tuned, polished, and optimized by Google's top engineers for years.
And was entirely built around standard LSTM cells.
And what Zoph and Le did here is almost brazen in its confidence.
It really is.
They made absolutely zero changes to the GNMT's underlying hyperparameter settings. They didn't retune the learning rates or adjust the dropout.
They simply ripped out the human-designed LSTMs, dropped the machine-designed nacelle in their place, and hit train.
And what happened?
Instantly, with zero tuning and zero human interference, the nacelle achieved a 0.5 BLEU score improvement over the standard LSTM on the translation test set.
They achieved a measurable, undeniable improvement in commercial-grade translation quality simply by swapping out the core architectural building block for one designed by an AI.
If we step back and look at the sheer scope of what we've discussed today, the legacy of this 2016 paper is monumental.
It really changed everything.
And the authors didn't hoard this discovery. They open-sourced their code. They officially integrated the nacelle into the TensorFlow library, making it accessible to any developer in the world.
This paper was not just a clever mathematical trick. It marked the dawn of automated architecture search in real-world production systems.
It proved, definitively, that machines had reached an inflection point where they could design better cognitive architectures for themselves than our brightest human scientists could.
It shifted the fundamental bottleneck of AI development. It was no longer about how smart is the researcher.
It became, how much compute do we have to run the search?
And you see that legacy everywhere in modern machine learning.
Oh, absolutely. While the specific reinforcement learning method they used in this paper was incredibly computationally expensive, requiring that massive cluster of 800 GPUs, it spawned an entire thriving subfield of research.
Right. Shortly after this paper, we saw the development of differentiable architecture search, or DARTs, which managed to make the search process vastly more efficient.
We saw NAS techniques applied to mobile development, actively finding architectures that maximize battery life on smartphones.
This single paper was the catalyst that basically shattered the assumption that human intuition was a necessary ingredient in network design.
It is a phenomenal, landmark piece of scientific literature.
Which brings us to my absolute favorite part of the show.
Here we go.
We have spent the last hour thoroughly grounding ourselves in the rigorous facts, the mechanics, and the history of neural architecture search. Now it is time to take off the lab coats, put on our tinfoil hats, and extrapolate into the unknown.
It is time for novel notions.
Right. As a quick reminder to you listening, the ideas discussed in this final segment are entirely theoretical. We are extrapolating based on the core mechanisms of the paper we just analyzed, but these are highly speculative research pitches intended for entertainment purposes only.
All right, I have two wildly ambitious ideas for you today, both deeply grounded in the math of Zoph and Le.
Let's dive into novel notion number one, which I am calling recursive meta-architecture search.
Recursive. Okay, I'm listening.
Here is the setup. We have just spent this entire deep dive marveling at the fact that a machine successfully designed a better neural network than a human. The controller RNN searched a space of 60 quadrillion possibilities and found the nacelle. But let's look one level up the hierarchy. Who designed the controller?
Well, a human did.
The paper explicitly tells us. It states that the controller RNN is a 2-layer LSTM with exactly 35 hidden units on each layer.
Yeah, researchers sat down and used their intuition to say, let's use an LSTM with 35 units.
I see exactly where you are taking this.
The outlandish idea is to apply neural architecture search to the NAS controller itself.
We construct what we will call a grand controller.
Let's ground this technically. This grand controller would utilize the exact same reinforced policy gradient mechanism.
And the exact same exponential moving average baseline function B to stabilize its learning.
But instead of outputting hyperparameter tokens for a CNN or a language model, the grand controller's target search space is the physical architecture of the subcontroller.
Yes. The grand controller searches the massive high-dimensional space to find the absolute optimal RNN structure, whose only purpose is to serve as the architecture searching controller.
So the reward signal R for the grand controller isn't the accuracy of one single image classification network.
No. The reward R is a measure of how quickly and how efficiently the generated subcontroller can find a high-accuracy child network on a proxy dataset.
So you are searching for an architecture whose intrinsic defining property is that it is exceptionally skilled at searching for other architectures.
Precisely.
And what is the impact if this thesis actually plays out?
This could trigger a literal AI singularity loop.
Oh boy.
If the machine designs a mathematically superior architecture searcher, that new hyper-efficient searcher could then be used to design an even better grand controller.
We could discover a fundamentally new class of search algorithm architectures, alien structures that don't look anything like LSTMs or transformers or any paradigm we currently understand.
Because humans fundamentally lack the dimensional thinking required to comprehend how a machine naturally wants to navigate high-dimensional space.
The entire field of meta learning would be permanently handed over to the machines.
It is entirely mathematically sound based on the principles of the paper. Although the compute requirements to run a reinforcement learning search over another reinforcement learning searcher.
Yeah, you wouldn't just need 800 GPUs. You would likely need the dedicated power grid of a small nation to run that loop.
But conceptually, it is a fascinating, highly logical extension of their work.
I knew you would appreciate the sheer scale of that one. Okay, let's bring it back to Earth just a little bit for novel notion number 2.
What's the second one?
I call this concept real-time dynamic architecture mutation, or RTDAM.
RTDAM.
Okay, here is the setup. The paper proved via that massive Google translation experiment that NAS architectures can transfer perfectly across tasks. They are robust, not brittle.
Right.
But right now, the standard paradigm in the industry is run the massive search, find the optimal architecture, train the architecture, and then freeze it in carbonite. You deploy a static, unchanging model into the real world.
But what if an architecture wasn't static after training?
This is a very pertinent angle.
Yeah.
Data in the real world constantly drifts.
It does. A static model trained to understand text data in 2016 will heavily degrade by 2026 simply because human language, slang, and context change over time.
Exactly. So here's the technical grounding for the solution. Imagine utilizing the paper's set selection attention mechanism, those content-based probability sigmoids that the controller uses to dynamically calculate skip connections.
Yeah.
But instead of using them once during the design phase, we leave them active and run them live in production.
As a deployed real-world model processes streaming data, we have a lightweight parallel NAS controller running continuously alongside it.
Right. And this live controller isn't rebuilding the entire network from scratch. Instead, it is continuously monitoring and updating the hidden state weights of those anchor points.
It is constantly recalculating the probability equations for the skip connections based on a rolling real-time reward signal of the model's live performance metrics.
So, if the deployed model detects a data drift, let's say the distribution of user inputs shifts significantly due to a trending global event, the live controller detects a sudden drop in the reward signal.
And to compensate for the new data distribution, it subtly alters the probability thresholds of the sigmoids.
Yes. The physical architecture literally mutates while it is running. It reroutes its own internal skip connections in real time.
The model might probabilistically decide this new type of complex user data requires deeper, more sequential processing. I am going to dynamically drop this shortcut connection to force the data through 3 more layers of convolutions.
It adapts its physical topology to survive in changing environments.
The impact of that on the industry would be seismic. It would completely eliminate the need for the massive periodic human retraining cycles that cost companies millions of dollars.
You wouldn't have to take the model offline, gather a massive new data set, run an entirely new NAS search, and deploy version 2.0.
The model becomes a living organism, constantly rewiring its own synapses based on the stimuli it receives from the real world.
It takes the static output of this 2016 paper and turns it into a continuous biological process of evolution.
A living architecture. It's an incredible thought.
It really is.
Well, that brings us to the end of our journey today. We have traced the evolution of AI from the tedious manual labor of human researchers drawing primitive edge detectors to massive computational factories building other factories.
All the way to the theoretical limits of living machines that rewire themselves on the fly.
We have seen how a brilliant, novel application of reinforcement learning allowed an RNN to navigate a dark space of 60 quadrillion possibilities to find a perfect architectural balance that the smartest humans on Earth couldn't see.
Thank you so much for joining us on this deep dive. As always, you can find the link to the original 2016 Zoph and Loeb paper in the description.
Read it. Marvel at the sheer ingenuity of the math. And before we go, I want to leave you with one final thought to mull over.
What's that?
As these NAS algorithms become infinitely more complex and efficient, they are generating architectures that are increasingly alien to human intuition.
Networks with bizarre layer sizes, asymmetric branches, and untraceable skip connections.
If the machines are building blueprints that we fundamentally cannot comprehend, what happens in 10 years when a critical piece of global infrastructure fails?
We will be relying on systems where no human engineer can read the code, visualize the architecture, or debug the logic.
Are we approaching a future where computer science stops being about engineering and instead becomes a kind of sociology, where all we can do is observe the behavior of the black boxes we ask to build themselves?
Something to think about.
Until next time, this is TalkTensors.